Alright, we're picking back up on part 2 of lesson 3, segment lengths and circles, out of the unit 3, circles and volumes unit. And we left off after the two tangent parts are congruent, two tangent lines from a common external point were congruent. Now we are looking at two chords intersecting inside of a circle. And if you notice, over here I'm pointing at this chord that has parts that are labeled as a distance of 5 and a distance of 12. So the chord, where the two chords are intersecting, right here at the intersection, it's creating two parts of each of the chords. And you can compare these parts by showing that the product of the lengths of the segments of one chord, so like if you were to take the 5 times 12, it should be equal to the product of the lengths of the other chord, of the segments of the other chord, so the 6 times the x. So in this case, if I were to use a highlighter to demonstrate this, you have a 5 and a 12 as two parts of one chord, and you have x and 6 as two parts of another chord. Now, if I go and represent that as the statement says up there, you have 5 times 12 equals 6 times x. 5 times 12 gives you 60 equals 6x. Divide by 6 and you get x would be 10. And notice that the two chords are not equal to each other, but their parts are comparable. And we're going to look at this further by showing that if you were to create some arbitrary lines here and here, what you would end up with is some congruent triangles. And we're going to, similar triangles. We're going to look at how these two triangles are similar and show that when you set up proportional sides, then you can solve for that missing side. In other words, in these two similar triangles, 5 is to 6 as x is to 12, and that's how you would solve that proportion. But we will look at that proof in class. And then if you turn the page, the last two things talks about if you have two segments meeting outside of a circle, or if you have a tangent. If you have a tangent and a secant, or two secants that meet outside of a circle. We saw back here when you had two tangents two tangents that intersect outside of a circle, they are simply just equal to each other. And then in this one we saw that when you had two chords meeting inside, you can multiply the two parts of one chord and set that equal to the multiplication of the two parts of the other chord. Now what happens when they meet outside is a little bit different. You have different parts of it, and if you look at this example, you've got a segment that is outside of the circle, the whole PR. You've got secant PR right here, and it has a length of 10 if you add the 4 plus the 6. That whole secant part from this side of this, from the P to the R, is 10. And so that's the whole secant segment. Now the outside piece is the part that is outside of the circle, is that QR right there. So we're going to say QR is a segment outside of the whole secant segment PR. Well, then we can look at the other secant segment where you've got this whole piece here is represented as the distance of x plus 5. If you add the x and the 5, those two pieces, you get x plus 5 here. and that would be the whole secant segment, TR. Well, outside of the circle, you have this piece, SR, and so you have outside piece, QR, that goes with the whole segment, PR. You have outside, all right, you have outside piece QSR that goes with the whole secant segment TR. Now, the formula for this, product of the length of one secant segment and the length of the segment formed outside, all right, what they're saying here is like in the first one, the product of the length of one secant segment and the length of the segment formed outside the circle is equal to the product of the length of the other secant segment and the length of the segment formed outside. So you multiply outside times whole, yellow, times pink. So outside times that whole thing is equal to outside times this whole thing. All right, now if I come down here, put that back, move that out of the way. All right, so QR we can see is equal to 6. Now that's the outside that's in the pink there. PR is equal to 10. You had to add the whole piece together, the 4 plus the 6 to get the 10. SR is 5 and TR is X plus 5. And since you're having to multiply 5 times the whole thing, you got to make sure you put it in parentheses. Now to solve this, make sure you distribute that 5 so you get 5x plus 25. And over here on the left you have 60. Subtract your 25, you end up with 35 equals 5x, and x equals 7. Now if I needed to know the whole length of TR, of course you would take the 7, you would take the 7 and you would go back and you would plug it in for x and add the 5 to get the whole length of TR. And lastly, the next one works very similar to this, except instead of having two secants that are crossing through the circle, one of these is a tangent. You have RQ here that is a tangent to the circle. Now you still have a whole piece, and just highlighted the wrong thing there. You still have the whole piece that is outside and is also tangent. So that is RQ, and I'm jumping ahead here. So RQ is a segment outside of the circle, but it is also the entire tangent segment. So it represents the outside and the whole part. So then if we look down here at, or look back up here, you have the outside piece RS, and I'm going to highlight that in blue. So RS is outside of the whole secant segment RT. And RT's distance should be represented as x plus 5 because you have to add the 5 piece, the piece that is a distance of 5, and the piece that has a distance of x to get a total distance of x plus 5 there. And so then when we come down here, we have the outside. We could do the RS is outside, and then the RT is the whole thing. So that's looking at the wrong highlighter. The secant part, you have the outside piece in blue, outside piece of that segment, RS, in blue. The entire secant segment is in green, RT. Now, for the hole and the outside of RQ, they both represent the same thing. So you have RQ times RQ. Let's try that again. You have RQ times RQ. RQ is both outside and it's the entire segment. So if I were to substitute the values for each of those, RS is 5, RT is x plus 5, RQ is 10, and RQ is 10. So you have 5x plus 25 equals 100. Subtract the 25, you get 5x equals 75, and then divide by 5, and you have 15. And that sums up the lesson 3 on segment lengths and circles. And then you will use these notes to create a graphic organizer in class. We will also go back and prove why these two create similar triangles, and we will then spend more time practicing all of these formulas. Thank you.